In this video, I want to talk about the D flip-flop. So if you remember from the previous video when I talked about the D latch, I said that in D latch, as long as the clock is 1, whatever value we have in D will be reflected or transferred to the output, which is Q. But I said that having this property kind of makes D latch to be a little bit problematic because it limits its capabilities to be used in synchronous logic circuits. In synchronous logic circuits, we usually require to have the process of storing new values in the components or in the flip-flops to happen only in a short period of time, not let's say half a time, which is usually the case for the D latch, because if we assume we have a clock that is 50% of the time 0 and 50% of the time 1, in 50% of the time for which the clock is 1, whatever change we make in D will be seen in the output or Q. So in synchronous design, we want to have a state element that can store values at specific times, not in a duration of some time. So that's why we come up with the design of the D flip-flop. So let's just go over the functionality of the D flip-flop. So the first important functionality that we need for the D flip-flop is to be able to sample D on a very short period of time. So here we consider either sampling D or storing D on the rising edge of the clock or on the falling edge of the clock. Because if we have a clock that looks like this, we have a region for which the value is 0, we have a region for which the value is 1, and we have this transition time, which is usually very small in comparison to the time that the clock is either 0 or 1. So we want this change or this storing process happen in this very short amount of time. So the same is true for the falling edge too. So if we have a circuit that can store the data in the falling edge, that is also preferable than the D latch. So for now, we focus on the D flip-flop that stores or samples D on the rising edge of the clock. So when clock rises from 0 to 1, D passes through Q, and otherwise Q holds its previous value. So again, we want Q to only change on the rising edge of the clock. So as you can see, this is the symbolic representation of the D flip-flop. If I draw the symbolic representation of the D latch, we have it like this. We have D on the left, and we have Q and Q bar on the right, and then we have this clock signal that is connected to the unit from top or bottom. So this is the D latch. So as you can see, this symbol for D flip-flop is mostly the same, except for this triangle that we now use here, which represents both the clock and the fact that this flip-flop is edge triggered. So either falling edge or the rising edge. So this flip-flop is only activated on the clock edge, not necessarily where the clock is 1 or 0, but when the clock changes from 0 to 1. So this short period of time. So sometimes it is common to have this flip-flop shown in this figure, a smaller figure, for which the left input is D and the right output is Q. So we usually don't represent Q because we know that we usually don't represent Q bar because we know Q bar is the complement of Q. So now that we have this, how can we design such a circuit? The answer to that is by using two back-to-back D latches. So here we have L1 and L2. L2 gets the clock signal itself. L1 gets an inverted version of the clock signal as the clock signal. And then we have the output of L1 to be acting as the input of the second D latch or L2. So again, you see this is a D latch. This is another D latch. So the combination or the configuration is we have a clock that goes to the clock input of L2. We have the complement of that clock signal to go to the clock input of L1. And then we have Q of L1 to be connected to the D input of L2. So now let's see what happens when we try to use this circuit. So when we have clock to be 0, that means the clock input of L2 is going to be 0, which means that the clock input of L1 is 1. So in this case, L1 is going to be transparent to the changes in D. So that means whatever value we have in D will be shown in Q. But on the other hand, L2 is opaque to the changes of D. So that means that whatever change we have in the value for Q won't be reflected in the output. Whatever change we have in the input D of L2 won't be reflected at the output Q of L2. So that makes D to pass through to this internal node N1. So whatever value we have in D will be in N1. So now let's say clock changes from 0 to 1. Let's see what happens. So we have clock changing from 0 to 1. So that makes the clock input of L2 to go from 0 to 1, which makes the clock input of L1 to go from 1 to 0. So in this case, L1 becomes opaque to the change of its D input. So that means that whatever change we have in the D input for L1 won't be reflected to Q. So we go from transparent to opaque. But on the other hand, for L2, we go from opaque to transparent. Why? Because when clock is 1, that means that the input clock of the L2 is 1. And you remember from before, we said that for a D latch, when the clock input is 1, then the D latch is transparent. So we go from opaque to transparent. So I show transparency with this arrow and then opaqueness with this X sign. So that means that whatever value we have in N1 now is reflected in Q. Remember, when a D latch is opaque, that means that it preserves its previous value. When a D latch is transparent, that means that it is basically looking at whatever input it gets in the D input of the D latch. So in the fraction of a second that go from 0 to 1 in the clock signal, these two D latches change their state. At the beginning, L2 is opaque, L1 is transparent. So that means that whatever D we have will be stored in L1. Right after we change from 0 to 1, L2 becomes transparent and L1 becomes opaque. That means that L2 stores whatever value that it has in its D input in Q. So you can think of this configuration as having a buffer, right? So this buffer is basically there to store the data and get rid of all the fluctuations that we might have in the initial data that we want to store. So let's just say you connect this into an output of a combinational logic circuit. You remember from before that, because of all the delays that we might have in our circuit, we may end up with some glitches in the output, right? Some unwanted output values. So this first D latch basically acts as a buffer to get rid of all those unwanted outputs that are caused by the delays in our circuit. At the time when clock goes from 0 to 1, and this is the clock signal is specified by us, right? So we have control over at what time we want to store our data. So we design our circuit in such a way that this clock signal has a frequency that ensures all those unnecessary or unwanted outputs are completely gone. Then at that specific time, we change the clock from 0 to 1, and that basically tells the circuit now is the time to store the data. So since this first D latch is now opaque, that means that the value in 1 does not change at all. Whatever we have in D, even though we may have it changed 1,000 times, it is not going to be reflected in 1. So that is why that is what I meant by sampling the D signal. We sample the D signal at a very short period of time. During the time the clock changes from 0 to 1. So because of this design, this back-to-back design, on the edge of the clock, more specifically on the rising edge of the clock, you can say this input D is passed to this output Q. So this is the design for the D flip-flop that helps us avoid one of the problems with the D latch, in which the output of the D latch would change as long as clock was 1. Now with the D flip-flop, we are limiting that and we make the circuit to be more synchronous. So we sample in a very short period of time from the input signal. So now that we have this, let's just go over the timing diagram of these two designs. We have the D latch on the left. So this is the latch. And this one is the D flip-flop. So let's just assume we have this clock signal that looks something like this, and then we have this D signal that is being applied to both of them. I want to know what is the output for each one of these two circuits. So first of all, let's just divide this clock into its consisting regions. So we have regions of the clock changing from 0 to 1. Also we have regions of the clock that is basically 1. So this is another region that the clock changes from 0 to 1. And this one is another region that clock changes from, clock remains as 1. So since our circuit or our D flip-flop is only sensitive to the rising edge of the clock, I don't segment the falling edge of the clock. Going from a design for a flip-flop that is sensitive to the rising edge of the clock to a design that is sensitive to the falling edge of the clock is very straightforward too. So if you change the place for this inverter, instead of having it being applied here, if you put it here, and then this one is replaced with a simple wire, then you have a flip-flop that is sensitive to the falling edge of the clock. But I leave that analysis for yourself to do it on your own. So now let's just see what happens in our circuit. So we have the clock signal to be 0, and then we have the value for D to be 0. So first of all, for the output of the Q latch, we know that when clock is 0, its output is going to be whatever it was before, right? So that was the functionality for memory. So in this case, since we don't know what was its value before, I just show it as both 0 and 1. So something like this, right? Since we don't know what is happening. When we go from 0 to 1, as long as clock is 1, then whatever the value for D, we see it in the output. So during this time, between this time and this time, the output Q is going to be exactly the output D. So what I do is that I draw it like this. So I just simply copy this part here. So we have here, and then we have this. So during this time, the output of the Q latch is going to be exactly the same as the value for D. After the clock goes from 1 to 0, the D latch remains at its previous value. So during this time, since the value right before clock changing from 1 to 0 is 1, the value for the Q latch remains as 1. So now we get to the second part for which clock is 1, and again during this time the output of the Q latch or the D latch is going to be exactly the same as D. So we have here D is 1, and then D becomes 0, and then D becomes 1 again, and then it stays at 1. And then during this time for which clock is 0, whatever change we have in D won't be reflected because the D latch is opaque to the changes of D. So D stays at 1 until the next time that the clock of the D latch becomes 1, in which whatever value we have for D will be reflected in the output too. So since it is 1, it remains at 1. So this is how we can draw the timing diagram for the output of the Q latch. So as you can see here in this region, since the clock was 1, whatever change we had in D was completely reflected in the output of the D latch. But now let's just see what happens with the output of the flip-flop. So as we said, for the output of the flip-flop, I just show it with this bold lines. So we only care about when the clock goes from 0 to 1, since we are working with the flip-flop that is sensitive to the rising edge of the clock. So again, before that, since clock was in 0, we don't know what was its output, so it can be both 0 and 1. But now, during this time, what is the value for D? During this time, the value for D is 0. So that makes that the output becomes 0. So even though after the clock goes from 0 to 1 in this period, right, in this time frame, the value for D changes from 0 to 1, it won't be reflected in the output of the flip-flop. Because again, the flip-flop, the D flip-flop samples D in the time that clock goes from 0 to 1, in the rising edge of the clock. So because of this, in this time frame, the value for D becomes stays at 0, even though, the value for Q, or the output of the flip-flop, stays at 0, even though the value for D has changed. And then this thing remains the same until the next rising edge of the clock. So until this point, we stay at 0. In the second rising edge of the clock, we have the value for D to be 1, which makes the value for the output of the flip-flop to go to 1. But again, after this rising edge, when clock is 1, even though the value for D is changing, the output of the D flip-flop won't change, because the D flip-flop only is sensitive to the value of D in the short period of the rising edge of the clock. So the value for D remains, the value for the output of the D flip-flop remains as 1. And this thing continues until the next rising edge too. So during the next rising edge, the value for D is still 1. So that makes this value to remain as 1. So as you can see, in the output of the D latch, we have several transitions that happen. So we have 1, 2, 3 transitions. And the main reason for that is the output of the D latch is more sensitive to the changes of D. Because half of the time, when the clock is 1, whatever change we have in D will be reflected in the output of the D latch. But on the other hand, for the D flip-flop, we only have one transition for the value for D. And that's because during the first rising edge of the clock and the second rising edge of the clock, so between the two, we only have one change in D, right? So in the first rising edge, D was 0, and in the second one, D was 1. And that is the only thing that will be reflected in the output of the D flip-flop. So this is basically the same circuit, but now based on this, you can see how the clock, whether the rising edge or the region at which clock is 1, can trigger the outputs of the D latch and D flip-flop. So as you can see, the output of the D flip-flop is only triggered by the rising edge of the clock, while the output of the D latch, not only it can be triggered by the rising edge, so not necessarily the rising edge, because we go from 0 to 1, you can say it is the rising edge, but more accurately, it is for when the clock is 1. So not only that, but also whenever you have changes in the value of D, you see it being reflected in the output as long as the clock is 1. So because of this, D flip-flops are more preferred for designing synchronous logic circuits. So in later videos, you will see how I will use D flip-flops in designing more complicated circuits that not only include flip-flops, but also other combinational logic circuits.